Hello, assalamu alaikum. Welcome to my YouTube series Numerical Analysis using C++ programming language. In this video, I will discuss the Newton-Raphson method, that how can we evaluate a root from a function. In my previous videos, I have discussed bisection method and second method. You can check it out on my YouTube series playlist. So okay, fine. Now I will start the discussions on Newton-Raphson method. Before diving into that, I wanted to discuss some basics about this Newton-Raphson method. Here is the algorithm for Newton-Raphson method. First of all, this solution exactly works using this process. We have to uh, evaluate the derivative evaluate the derivative of our given function. Then as if we say xi is our initial guess, then we will get xi plus 1 using this formula. Okay, x minus f of x divided by f prime of x, and after this we will calculate the error value. If this error is our desired less than our desired error, then we can get the solution, that will be xi plus 1. Okay, so this is the process. Compare the absolute relative approximated error. If our error is greater than the given error, so we have to iterate the problem again, and if this is not, then we will stop this algorithm. Okay, so this is a problem example. I will solve this example using C++. So as this is our problem, given that function is x cube minus 0.165 x square plus 3.993 into 10 to the power minus 4. Okay, so let's see how this problem has been solved here. Here f of x is given, and then f prime of x is evaluated by derivative of f of x 3x square minus 0.33x. Then the initial guess was 0.05. In iteration number 1, 0.05 minus f of x divided by f prime of x naught, that is 0.05 and also 0.05. So in that case, we have evaluated one value for x1, that is 0.0624. Okay, and again this after this value we have evaluated another problem. We have evaluated this error value. This is almost 19.90. Then we are going to the iteration number 2, then iteration x2 equal to x1. This process is happening again and again till we are getting the error almost 0%. Okay, so I will solve this problem using C++. Okay, this is my C++ interface. I will open these two figures. Okay, I'm solving this problem, so that's why I have just showing my problem in my right side my screen, and in the right side I will develop the program for this problem. Okay, so I think that would be helpful to understand the problem. So first of all, we have to start with the header files. That would be very common, include stream, include an IP, include the library. Okay, so now I am using namespace std my main this is my header file problem. Sorry, this is my header file. So now I will disclose our function double f double x that will return the value for return power f x comma 3x cube minus 0.165 into x square plus 3.993 and e minus 4. Okay, that's my one function, and I have to differentiate this function again. So I want to take another function, that is df, differentiation of f. So this would be 3x square minus 0.33x. okay, so I'll go for this 3x square power is square 3x square minus 0.33x x. Okay, that's all. Now I want to get into the main function, that would be disclosing the variables a, b, and e for error. That's all. Error. Now I want to take the value for cout and the first initial guess in a. I think it's working. Okay. Out under the error value. Now we want to check if that can be happen that we just guess the right value or the right solution for this function. So in that case the solution will be printed out. So that's why I am adding this conditional loop. If my initial guess is totally equal to the solution, so I want to print that the solution would be value for a. So that's very rare case, but whatever, I want to complete this code, that I want to develop this code for the complete solution. If in any case we guess the right value for this function, so that would definitely show that the solution is a. and if this is not, then we will further proceed to the Newton-Rhapson method. So that's why I am just adding this conditional loop to make it more clear. The solution is A equal to A. Okay, I think it's okay. Okay, it's working. Now I want to check another. So now we will dive in the further loop that would be my error value. Okay, so this is my first iteration that will evaluate the value for B, using the initial guess A. So in that case, I want to evaluate the value for B first. A minus f of A divided by df of A. Now I need to check this error value. Okay, if this error is satisfied with my desired error, so my solution would be B, and if this is not satisfied, then I have to go further iteration. So in that case, I am just adding this error value in this condition while loop. Okay, so that would be absolute value of B minus A into 100 to 100 divided by B. Okay. If this value gets greater than my error, then we need to go for further iteration. So that's why I have used this greater than symbol. Okay, so I am starting this loop, second bracket is there. So as I have already evaluated the value for B and the value for A, so already I have done this iteration process first time. Okay, in this process, in this line, so I have done this iteration 1, x1 equal to x0 minus this value, that f of A divided by df of A. So, and in that case I have checked this error. If this error is greater than absolute value for is greater than our error value, so I need to go for further iteration. This is iteration number 2. So in that iteration number 2, my new B, this is my B, so I have to, this x1 would be my this x1, right? So that's why I want to swap the value in A, this equation, this A to this value like this, A equal to B, and then I will evaluate this again. So in that case, this B value has been assigned to A, and now I will get another new b value. Okay, so that's my point. Oh, okay, so I want to plot all these value in my chart, so that's why I am using this iterations that w 15 a n b w. This is not necessary, but if I plot this chart or this table, this would be helpful for me to understand the whole problem. That's what exactly and how this problem, how this code going to happen in this solution algorithm. So that's why I'm adding this chart here. Okay, I want to start this chart here. Okay, so adding this chart, I'm just evaluating the value for a and b. So iteration plus plus. I think it's okay. Then our solution would be Cout the solution is p equal to I think it's okay now. Okay, this iteration, sorry, I didn't define these iterations here. So int iteration zero point zero 0.050. Okay, sorry, actually it's not working. I have to just some formatting issue, so I'm just fixing it out. In that case, I use inline and also here that line. So I think that would be 0.050. Okay, it's working good. There is need something more formatting issue. Okay, fine. This is 25. 50. Zero 5 0. Okay, I think it's working fine. Just final attachment, and also I want to add this error value. Here is equal 0.0580. Okay, so it is saying that our solution is 0.062337776, and I think there is our value. Yes, 0.06233 our 776, that was 776. Here this x3 value showed as 0.06238. Okay, so our problem is done. Now I want to add something more organizing factor in this coding that will make this code completely fine, because if I put this value for a0 and error is 0.001, then my solution would be minus infinity. Why this happens? Because in that case here we are evaluating this x1 or x2 value using f prime of x, right? So in our case, if x is 0, so differentiation of function x would be 0. So in that case, that would be totally infinite value. So that's why I want to add something condition here that will eliminate this issue in this program. Okay, so that's why I want to take another loop while that will be true. Why true? I am just saying later. This second bracket, if f is equal to, the solution is okay. Here I want to add another value, else if df of a is 0, then our program should be, our value is not okay for the Newton-Raphson method. So I want to add this. Let's see how. Derivative value is 0. Try another value for a. Okay, so that is my while loop started from this point. So I want to finish this loop here. I will explain why I use true value here. else break. Okay, my while loop is closed. Okay, and when I am using this true value, that means whenever these conditions are true, then this loop will be happened again and again. If df is equal to 0, the solution would be a. Oh, sorry, here I didn't add another thing, that is I have to terminate this problem here. Okay, if I already got the solution, so I have to terminate the program here. So that's why I want to add return 0. So our program will be terminated here. So if this happens, okay, that will be terminated. If this also, else if I have added this condition df, my derivative function at that value is 0, so my derivative value is 0, so I have to take another value for a. So if this is happens, if this condition is true, this loop will happen again and again. And if this and this are not true, so here else break, that means this loop will be break here and go to this further procedure. Okay, so that's the fact. Now I'm checking it out again. I'm checking 0 and putting the value for 0.01. Yes, it's saying derivative value is 0. Try another value for okay. I am now value for 0.05 that was mentioned in my problem. The first value was 0.05 and I would enter the value for error. Okay, it's already my iterations value. That is 0.023776. That's my answer, which is completely aligned with this problem 0.0238. This is for precision. Okay, 0.062377 is rounded to 8. Okay, so that's my problem. So in this procedure, maintaining this code, you can perform this Newton-Raphson method. I want to show something in this code. Okay, if I guess the same value for the answer value for this problem, like 0.06238 and the value, so this will perform this value 0.023776. okay, I want to as the root for this function is 0.0623776, so I want to add this value for initial guess. Let's see what happened. 0.0623776, 0.01. So the solution is 0. It's working well. Okay, so that's all for today. If you like this video, please stay tuned and subscribe my this YouTube channel. Thank you.